In this topic, we are going to cover project number 4, buffer overflow. Project number 4 is a bit of a wildcard project for this Python 201 for Hackers course. The purpose of this project is to show, by example, how you can use Python to solve binary exploitation tasks by leveraging the Pawn Tools module, which was demonstrated during the Python 101 for Hackers course. For this lesson, we are also going to be using a Linux virtual machine rather than a Windows machine. Python is cross-platform. However, different modules have different support in different operating systems. When working with pawn tools and hacking vulnerable Linux binaries, it's easier and more efficient to work in a Linux environment. To get started, we first need to have a problem to solve. For this lesson, we will be using the unexecutable stack challenge from 247 CTF. So let's start by downloading this. And we can also start the challenge. And now that we've downloaded the binary, we can unzip it. And we can mark it as executable. Next, we can import from Pawn Tools and get started. Reverse engineering is outside the scope of this course, but this challenge is just a classic overflow with an executable stack. So to solve this problem, we can overwrite the instruction pointer and then return to the stack in ESP, which is where the shellcode is stored because it's the next item on the stack. So let's set up our context and get started. And we need this context because we can see that this is a 32-bit binary. Next, we can specify the process. And the first thing that we need is a cyclic de Brouwer pattern to find our offsets, which we can then verify using GDB. So let's do that. Create our cyclic pattern. Send it to the binary. We can execute this. And here we can see that Pawn Tools has attached GDB to our process. It's then continued the process. It's then sent our cyclic pattern to the process. And here we can see the error that we now have a segmentation fault. And we can see in the registers where our segmentation fault has occurred here for the instruction pointer. And we can now use cyclic find. And we can see here that the offset is at 140 bytes. And now that we know our offset, next we want to identify how we can jump to ESP, which is the location where our shellcode will be in memory. So let's comment this out. And to do that, we can load the binary as an ELF and search for a jump ESP instruction. Jump ESP. And we can verify that we can find this instruction. And we have. And now we have all the pieces that we need in order to solve this challenge. We can use flat to send our padding of 140 bytes. then our gadget to jump to ESP, and in ESP, we can write our actual shell code which we want to execute. So we can send 140 A's, followed by jump ESP, followed by our shellcraft.sh, and we can test our exploit locally. And now we can see that we have an interactive shell, and we can also verify this on the server. So instead of opening a local process, we can instead say a remote connection, copy the address, specify our port, and we can execute this now. And so now, rather than being a local process, we're now talking to the remote server. And we can see that we have a shell and we now have access to our flag. In this lesson, we have shown how you can use Python and the Pawn Tools library to solve binary exploitation challenges and tasks by interfacing directly with the debugger, finding gadgets in a vulnerable binary, and hacking vulnerable applications both locally and remotely. But that's it for now, and in the next lesson, we are going to cover project number 5, Encrypted Bind Shell.